Okay, so welcome back, Unit 4, linear momentum. Now we're going to focus on conservation momentum. Remember, in mechanics, there's 3 conserved quantities that we focus on. In Unit 3, we talked about conservation energy. In this unit, we're going to look at conservation momentum. And then when we do rotation, we're going to look at conservation of angular momentum. Okay, and so this is where we're focusing on collisions and so forth. And so the concept of momentum is particularly important because if no net external force, there's our little caveat, right? Didn't go far enough. So if there's no net external force exerted on a system, the total momentum of the system is a conserved quantity. So that means it doesn't change. So mathematically, it's like my before momentum equals my after momentum. Okay, and when we say that, we mean total momentum, not just individual momentum. Okay, so here, right, my total momentum between these two objects will be equal to my total momentum between those two objects, right? And so same thing when you do here, even though this is at an angle, my total momentum here would equal my total momentum there, even though they go off at angles, right? And so here we talk very briefly about systems, right? So again, a system is simply a set of objects that are chosen which may interact with each other. And so there's 3 types of systems: open, closed, isolated. This is ideal. This is more real world. Okay, well, these 2 are more real world. Okay, so open system, energy and matter allowed to flow freely in and out of a system. Closed system, energy can flow freely into the system, but matter cannot. Isolated, nothing goes in or out. Okay, so when we talk about like conservation momentum, we talk about no net external force. We make the assumption that our systems are isolated. Okay, so isolated systems goes back to that idea that there's no net external force. All right. Now, when you're doing these problems with collisions or explosions, right, always start here, because on the AP test, they often will add, they'll award points, not reward, but award points if you just simply write down what's the big concept or the big idea that is being used for this particular question. Okay. And then you just kind of keep going from there. So like if I was to do my total momentum before, I would have MAVA plus MBVB, right? So these are vectors. So technically this would be a negative. So, if I'm just looking at magnitudes, I would have MAVA minus MBVB. And then afterwards, again, MAVA prime plus MBVB prime, right? But if I'm looking at magnitudes, MA is now reversed its direction, and MVB is going in the positive direction. Okay, so what I would do is these 2 equations are set equal to each other, and then I would solve for whatever I'm looking for. Okay, I'm not going to go diving into the 2-dimensional one there, but it's the same idea. Okay, that my x components, right, would essentially equal my before, and my y's would cancel out because there was no y momentum to start. Okay, so that would allow me to find velocity or speeds, and then trace it back to be able to find if I'm looking for the speed after or before. All right, so let's look at 2 examples. Okay, so the first example, you have a 10,000 kilogram railroad car traveling at a speed of 8 meters per second, striking an identical car which is at rest. If the cars lock together as a result of the collision, what is their common speed just after the collision? So again, P before equals P after, right? Always start by writing that down, because on the AP test, they're probably going to award a point there. And now I'm going to write down I have two objects. So my before momentum is just simply from car A, right? Because it tells me that car B is at rest. So I don't have to write that down. And that's going to equal, now they're going to hit and stick together, which tells me that there's one big mass. And they even say it right here, there's a common speed. So that, what does that mean? That after the collision, these two stick together, right? And go off at one big common final velocity. Okay. And now this VF is what I'm solving for. So now I do my algebra and find that VF is MA VA initial divided by what amounts to my total mass. So now I can plug in those numbers. 10,000 times 8 over 10,000 plus 10,000. And so I get 80,000 over 20,000, which tells me that my final velocity is equal to 4 meters per second. And guess what? It's not a coincidence that it's half, because they're equal in mass, right? If they were different masses, my final velocity would not be half of my initial, right? And that only works out is because my two objects are the same size, okay, as they collide. The next one's a little bit of a special case. So a lot of times you'll hear like these fall into this conservation of energy or conservation of momentum, but this is what we call an explosion. And yes, it happens to use a rifle, right? It could be two lab carts tied together by a string, right? That string is cut and springs are activated and they go off in opposite directions. It's the same scenario. I've seen questions where it was, a torpedo shot out of a submarine. Okay. We just know that whatever we're looking for, we're probably going to get a negative speed, right? A negative velocity, because one's going to go one way. Like in this case, the bullet's going to go one way. The rifle's going to go the opposite direction. Okay. This is recoil, right? This is the reason why when you shoot a gun, it kicks back. Okay. And so again, I start with P before equals P after. Now, the good thing is before, it says right there, everything is at rest. So my before total momentum is 0. So everything comes after the firing of the rifle, right? And so I have the bullet and the rifle going back, going in opposite directions, which means one of those velocities is going to be 0, or not 0, but negative. And so if I solve this for VB, I get velocity, right, in this case, we're looking for the rifle. So the velocity of the rifle is equal to MAVA, which is our bullet, negative MAVA, divided by MB. And so I say negative 0.020 kilograms. Now, again, a lot of times when it comes to a bullet, they'll actually give it to you in grams. So you need to convert. And that's shot off at 620 meters per second. And it's coming out of a 5 kilogram rifle. So I plug in my numbers in the calculator and I get a velocity, right, of the rifle. The recoil velocity of the rifle is negative 2.5 meters per second. So what does that mean? Bullet went to the right, which you see here is the green arrow. Rifle goes to the left. And you can see big arrow for the bullet, small arrow for the rifle. Okay. So this kind of starts talking about our collisions, which is the next video and the end of the chapter. But our example for a collision, we're going to talk about a special type of collision centered around